All right, so we're going to look at a forced mass spring. First of all, I just want to explain in a mass spring. So the M would be the mass that's attached to the spring. That's the little red piece here. The spring is here and it's attached up at the top. K is the spring constant and B is the damping coefficient. So if B is 0, we have an undamped spring equation. If we start this at some initial condition, maybe we pull or stretch the spring down, then we should get then just a start, and the spring just oscillates back and forth, creating an ellipse or a center in the phase portrait. And then of course the graph of the position function is just a sine or cosine curve. So let's say we add a little damping. Let's just add like a coefficient of B as being really small, like 1/2. So very little damping. Let's clear this and we'll start again. And I just want us to, so this is called the dash pot down here, and it's going to have the effect of the damping on the spring. So we're just going to have our damping coefficient at 1/2. If I start this again, maybe we push it down so far and let it go, and we notice we do get an oscillation that dies down to 0. So in this case, if you were to look at the square root of b squared minus 4mk, this would give us complex eigenvalues, which gives us an underdamped system. And we could start this with any kind of initial conditions. It's going to die down to 0. You see oscillations here. In the position function, you can see it oscillating here, and it also has, in this case, counterclockwise rotation. But basically, this graph here is our phase portrait. We can use this to graph our phase portrait with orientation here, and then here's y of t. I'm not graphing the velocity function, but so that's with very little damping. We're going to get some oscillations, but it will die down to 0. Those are complex eigenvalues. So let's do an overdamped system. So if we let B, the damping, increase, so it's overdamped, and I'm going to use 2.5 here. If I can get on it. There we go. Let's clear this. And now this is overdamped, so we shouldn't see any oscillations. And if I start, anywhere, basically pulling it up or whatever and letting it go, we should see no, and I'll just stop this. You notice it went right down to 0, and it just continues along to be 0. So it damps, but there's no oscillations. One of the things with this, with an overdamped, we do get two straight line solutions. Two real eigenvalues. So the straight line solutions would be on the line y equals negative v. So if I start really close up into this corner, I should get a pretty straight line right down to 0, because that represents our one of our straight line solutions. And you notice the damping just exponentially goes down to 0. This is actually exponential with speed e to the negative t. And then the other straight line solution with the other eigenvalue of negative 4 for this system would come across on the line y equals negative 1/4 v. So if I get this close to negative 4 for v and 1 for y, I should get really close to, again, a straight line going right to the origin. If I try that over here, again, a straight line. So this kind of represents our two straight line solutions. The eigenvalue is negative 4 for this eigenvector. So the solutions are going to actually come in parallel to the larger eigenvector in this case, or the larger eigenvalue, the associated eigenvector with the largest eigenvalue. So the solutions are going to come in parallel to the eigenvector on the line y equals negative v. So we can actually plot a few of these solutions. You notice they come in parallel to that. And when I plot a few of the solutions, this actually gives us our phase portrait. So you can get an idea what the phase portrait would look like with two straight line solutions. And then again, when we see we don't see any oscillations, so this is over damped. Now, critically damped is when the m squared, or excuse me, b squared minus 4mk is equal to 0. And that's going to happen when b is equal to 2. So I'm going to put this back at b equal to 2. Clear this, and now this we get a repeated eigenvalue. So we get one straight line solution. So for this system, the repeated eigenvalue is negative 2, and the associated eigenvector is along the line y equals negative 1/2 v. So if I get as close as I can to that line, 2, negative 4, I should get a solution that tends right to 0 on that line. Again, I'll try and get as close as I can, right about there. And so this is our one straight line solution. And all the other solutions are going to like fake spiral into this. So if I start somewhere else, I'll notice that I'm going to get a spiral but no oscillations. So everything is spiraling. It's a fake spiral into that solution. So again, a critically damped has one repeated eigenvector, has one straight line solution, so it's like a fake spiral. Again, this is counterclockwise going in. So next, I'm going to look at what happens if we add an external force.